in this video has to do with some background information on the bathtub model, the water quality model. Following the background information that will be given, I'll go through an application of the model for Medicine Lake, which is in the western suburbs. A bathtub is a lake and reservoir water quality model that was developed by the U.S. Army Corps of Engineers. The purpose of that model was to help to evaluate the impact of water quality or contaminant inputs or pollution inputs, nutrients mainly, inputs to lakes and reservoirs and the effect of those on the quality of the lakes and reservoirs. It simulates steady state flow and transport conditions in lakes and reservoirs. While it's doing that, it also simulates eutrophication conditions within the lake, within the water body. So it calculates water balance and also nutrient or chemical balance, and then provides information so that the user can determine what the eutrophication status of the lake or water body happens to be. Of course, eutrophication can be defined as the nutritional enrichment of a water body, which generally leads to an excessive production of organic materials by algae and other aquatic plants. The model performs steady-state water and nutrient balances for spatially segmented hydraulic networks. And through this, it accounts for advective and diffusive transport and also nutrient sedimentation, or basically the deposition of nutrients out of the water column. It predicts water quality conditions, including total phosphorus, total nitrogen, chlorophyll A, transparency, and hypolimnetic oxygen depletion. And of course, all of those things just mentioned are related to the eutrophication condition. I might also mention that on that slide it was stated that the model simulates steady state flow and transport conditions. It actually does allow you to look at transient changes in water storage or lake water level. Generally, the model is used for situations where the water level doesn't change over time, but the model does allow the condition where the lake water level is changing over time, which would imply not a steady state, but a transient flow condition. The input requirements are the characteristics of the watersheds and tributaries that are contributing the runoff, and contaminants or nutrients to the water body of interest. Basically provide information about the watershed area, and for tributaries it would require the volume of inflow to the lake or reservoir, and then also the concentrations of selected constituents. For the characteristics of watersheds, you can provide detailed information about the land uses that appear on a watershed, including the fraction of a particular land use or the different land uses happen to be in the watershed. It requires inflow from, let's say, entering into the water body from the tributaries, and also the quality of the water. So you'd be inputting the chemistry information for that inflow. The input data can be would generally be based on monitoring data. It could also be derived from some sort of a hydrologic model. Doesn't have to be monitoring data. And those data could, if it's monitoring data, it could be evaluated using the flux model or some other similar model. Some possible models that could be used to generate input, not monitor data, but actually synthetic input data. Could be the SWOT model, P8, GWLF, or some other type of model, such as HSPF, for instance. Bathtup also has an internal algorithm that allows you to compute runoff and nutrient loads rather than having an external model do that, a model like SWOT or P8. Bathtup has the ability to take watershed characteristics as input by the user and to compute runoff from different areas of watershed and also determine the nutrient load that comes from those areas that are going to enter into the lake or reservoir. The inputs require, or an input is the bathymetry of the lake or reservoir. Basically, the information about how deep the reservoir is. And of course, you need to know the surface area of the reservoir as well. And then the lake or reservoir water quality data that has maybe been collected over a period of time. So you might want phosphorus concentration, nitrate concentration, Secchi disc readings to look at clarity, water clarity, and then also chlorophyll A concentration. You can use information such as temperature and oxygen profiles to come up with that lake water quality information and phosphorus profiles. And then the chemical characteristics of bottom sediments, since those sediments can be a source of internal loading of a particular chemical to the volume of water in the lake, it's important to know what the chemistry of those lake sediments happen to be. The outputs from the model are tabular and are basically a tabular output or graphical display of information on what is calculated by the model for different segments of a particular water body or series of water bodies. It calculates the water balance and also the nutrient balance for the water body or series of water bodies that are connected to each other. It predicts the nutrient concentrations in the water bodies. It'll calculate the transparency of the water, chlorophyll A concentrations, total phosphorus concentrations, nitrate concentrations. It'll determine nitrogen or the oxygen depletion level, and then also for all of these things, it'll calculate statistics on the parameters that are calculated. So you get a mean value, but also get some statistics on the range of values, since inputs are given as being not particular values, but a range of input values for certain parameters. And so the outputs would also have a range of output values. The models associated with the Bathtup model are Flux, which we've used in class, and then also a model called Profile, which has to do with profiles of oxygen, temperature, and phosphorus within a lake or reservoir. The basic structure of the Bathtup model is you've got inputs. You have the model that takes those inputs and translates them or transforms those inputs into an output. The model does allow for some error analysis, so the inputs can have a range of values. So, for instance, rainfall you could input the mean value of the rainfall over a period of time, and then you could give upper and lower limits, what the range of that rainfall should be or could be. Other parameters might be parameters related to the uptake of nitrogen or the deposition of phosphorus within the lake, parameters that determine that process of fate for the nutrient. And if you put error bounds on those parameters, then of course the outputs will have those error bounds on them. A few details showing the inputs are listed here in summary, so you can see some of the inputs that I've already mentioned. Those inputs are used with the model to generate the outputs that are shown on the right-hand side. A reservoir or lake can be represented by one of the schemes that is shown here, so you don't look just at maybe a single lake. You might have a lake that's made up of a main body and then a bunch of maybe several bays, and so you can treat those bays as separate segments. And so here it's shown that you can have a series of reservoirs. You can have reservoirs in parallel and so forth like that. And these are the possible schemes that you could use the bathtub model for to represent lakes and reservoirs. For guidelines on the segmentation of a water body, each segment is defined by area, mean depth, length, mixing layer depth, hypolimnic depth, and observed water quality if it's available. A lake or reservoir is subdivided into separate segments if the conditions are variable enough to warrant it. So, as I mentioned before, if you have a lake that's got a number of bays, the bays are generally going to be shallower than the main body of the lake. So the characteristics of what goes on in those bays would probably be much different from what they are in the main body of the lake. And so you might want to break that lake reservoir up into several segments. But each segment that you define then needs to have all the information that's given in the first bullet point that's shown here. So here's an example of a segmentation. This is for Lake Keystone. You got the Arkansas River coming in on one side, you got the Cimarron River coming in from another point, and then there's a discharge point on the lower right-hand side. And so this is could be almost looked at as being both lakes are flowing into a reservoir, Lake Keystone. The reservoir could be looked at as being a flow-through lake, for instance, or it could be looked at as being a true storage lake. In any case, you can see how the lake has been broken up into several segments using the ideas that have just been talked about. Some of the limitations of Bathtup are shown here. Certainly would not be limitations on anything that we do, because the dimensions that are allowed here are quite generous. So number of segments is 50, number of tributary or outflow streams is 100. Number of transport channels, those would be channels between different segments, is equal to 10. And the number of land use categories that you can use in the case where you use the model to calculate runoff and nutrient loads rather than using monitoring data. There, the number of different land use categories that can be characterized is 8. The equations for the bathtub model are shown here. These are very basic equations that are used to calculate the water balance and the chemical balance. So the first equation is the one for the water balance. Capital V is the volume of water in the segment. Qn is the flow into the segment. Q out is the flow out of the segment. P is the precipitation falling directly on the segment. Capital E is the evapotranspiration, or the evaporation off that segment. And the minus plus L would be exchange of water between that segment and groundwater underneath that segment. Capital A is the area, surface area of the segment. The second equation is a chemical balance equation. It looks very similar to the water balance equation, but instead the variables fluxes and volumes are multiplied by the concentration. So C sub L is the concentration of the constituent, total phosphorus or nitrate or whatever, in the lake or reservoir at a given time. C in is the concentration entering in with the inflow water. C out, well, it's not really C out, but CL again is the lake water concentration, and that would be the concentration of that chemical in the water that's leaving the lake, Q out, or leaving the segment. So the one main difference between the chemical balance equation and the water balance equation is that we have an additional term, which is minus plus S times A, and S is the source or sink of the chemical that we're interested in within the system. So it could be dropping out of total phosphorus might be depositing out of the water column, and that would be a negative source or a sink, let's say, of that chemical out of the system. The units for each of these variables is given, or I should say the dimensions of each of these variables given in this slide. Just some sample equations. You can, in using the bathtub model, you can go to the help menu and you'll find exactly this type of table, which gives details on the different kinds of chemical processes. This one's for the phosphorus sedimentation, basically how the phosphorus within the water column might deposit out of the water column. And there's a number of different selections that you can make for the type of model that you want to use. And so we'll be using equation number 9, for instance, in some of our applications. So, and some details on this, but you can look at from the user's manual, which is online with the bathtub model, you'd be able to look at these equations and in more detail. Okay, so as I already mentioned, Bathtup actually can do unsteady flow. Generally, Bathtup is applied with this. However, Bathtup is usually applied with the assumption that everything is steady state, which of course means that for the water balance, there's no change in volume of the lake, and also there's no change in storage of the chemical within the lake. So that basically makes any term in the equations that would be derivative with respect to time is going to be 0. So the left-hand side of those two balance equations, the water balance equation and the chemical balance equation, both go to 0 for the case where we're looking at steady state flow. And this is the general equation, this is the equation that's usually used in most applications. Some scenarios that one might look at with Bathtup. Scenario A would be where you have an existing reservoir, you have water quality, or you have water data and, I should say, water balance data and nutrient balance data available to you. And you also have the data that describes the quality of the water in the lake or reservoir. B would be, again, where you have an existing reservoir, but you don't have data on the input water or the nutrient data, but you do have data on the quality of the water in the lake. And third scenario, C, is where you have either an existing or proposed reservoir, and you have the input water quality data and water balance data, but you don't have pool water quality data available to you. So those are possible scenarios that one might want to look at. Okay, and with that, I'm going to finish this video, and we'll publish a separate video or prepare a separate video on this application of the bathtub model to the Medicine Lake phosphorus TMDL.